Hello there, and welcome. I am the sleepy astronaut. I'm so glad you found your way here. Maybe you have had a long, exhausting day, or you just enjoy drifting off to sleep floating in space. Either way, tonight's journey is for you. I have a special treat for you tonight, one of my favorite cosmic phenomenon. As the Earth goes to sleep, we will be drifting toward the deepest, strangest abyss in the cosmos. Black holes. These invisible giants represent the ultimate breakdown of human understanding, where the laws of physics simply shatter into the dark. We know they are born from the violent death of massive stars, collapsing into a point of infinite density wrapped inside an inescapable horizon. Yet, how they truly operate at their absolute core remains one of the greatest, most haunting mysteries of the universe. Time bends, space curves infinitely inward, and reality itself vanishes behind a veil of absolute blackness. It is a concept so utterly alien and terrifying that it completely defies the human imagination, making it the perfect place to lose yourself tonight as we drift through the silent void. If you enjoy these calm journeys through space, I invite you to subscribe or leave a thought below. It helps other astronauts find their way here. But for now, your day on Earth has come to an end, and your journey through the stars has begun. You don't need to do anything, just relax and let your body sink, let your eyes grow heavy, and allow your mind to drift into space. Let's take off. To truly understand what separates a black hole from every other object in the cosmos, we must first unlearn how we visualize the universe. When we gaze up at the night sky or look through the lenses of our most powerful telescopes, we see stars, planets, nebulae, and galaxies existing within space. They are massive, glowing or rocky structures floating upon the grand, stable stage of the cosmos. A planet is made of rock and metal. A star is a raging fusion engine of plasma. A nebula is a sprawling cloud of dust and gas. But a black hole is fundamentally different in every possible way. It is not an object residing in space. It is a catastrophic failure of space itself, a literal puncture or bottomless tear, ripped deep into the fabric of reality. To picture this, we must think of space not as a vast, empty nothingness, but as a flexible, dynamic fabric woven across the universe. Every normal object with mass, a pebble, a human being, a mountain, or a shining star, places a gentle weight upon this fabric, creating a slight dimple or curve in space-time. This gentle slope is what we experience as gravity, keeping our feet on the ground and holding planets in their orderly orbits around the sun. But a black hole is something far more radical and extreme. When a massive star collapses under its own immense weight, it does not just form a dense ball of matter. It crushes that matter so intensely that it overcomes every known force in nature. The atoms are stripped of their structure, the empty space within them is completely erased, and the entire mass is compacted into a single, infinitesimal point of zero volume, known as a singularity. When mass is concentrated into a zero-volume point, the gentle dimple in the fabric of space-time transforms into an infinite vertical cliff. The local curvature of space becomes so severe, so impossibly steep, that the fabric tears open entirely, creating a bottomless abyss from which nothing can ever return. This is the defining characteristic that separates black holes from everything else in the universe. Normal objects push back against gravity using internal pressure, whether it is the thermal radiation of a star or the electron degeneracy pressure of a white dwarf. But a black hole offers no resistance whatsoever, because its internal geometry has turned completely inward upon itself. The mass has vanished into a point, leaving behind only the permanent, gaping wound it carved into the geometry of the cosmos. This profound distortion breaks the normal rules of geometry and causality that govern our everyday existence. In the normal universe, space has 3 dimensions, and time moves forward in a steady, unyielding march, allowing us to move left or right, forward or backward, up or down. But as you approach the core of a black hole, the extreme warping of space-time becomes so severe that the dimensions of space and time actually swap places. The singularity ceases to be a spatial location that you can point to in a room. Instead, it becomes a moment in your future that you cannot avoid, just as surely as tomorrow follows today. Trying to move away from the singularity inside a black hole is as futile as trying to stop tomorrow from arriving, because every direction you point, your ship simply leads further down the inescapable slope. For centuries, this bizarre geometry has fueled some of the wildest concepts in theoretical physics and science fiction alike. Imagining black holes as cosmic tunnels or portals leading to distant galaxies, parallel dimensions, or alternate universes through hypothetical structures called Einstein-Rosen bridges or wormholes, while modern theoretical physics suggests that traversable wormholes are likely impossible due to extreme quantum instabilities and the violent internal dynamics of actual collapsing stars. The mathematical possibility alone reveals just how deeply strange these objects are. They represent the absolute boundaries of human knowledge, the exact point where our 2 most successful descriptions of reality, general relativity, which governs the massive cosmos, and quantum mechanics, which governs the subatomic realm, collide and shatter into complete contradiction. Once matter or light crosses the outer threshold of this gravitational abyss, it is permanently severed from the rest of the universe. It cannot send signals outward, because any photon of light it emits is dragged relentlessly backward down the steep slope of space-time, unable to climb out of the well. This creates a stark, absolute separation between the interior of the black hole and the external universe, wrapping the central mystery behind a one-way membrane of pure, inescapable darkness. Whatever falls inside is erased from our reality, locked away forever in a localized pocket of space-time that is completely cut off from the rest of creation. The grand cosmic contrast becomes even more striking when we consider how these dark titans reveal their presence. Normal astronomical objects are defined by what they emit: starlight, infrared radiation, radio waves, or X-rays. They announce themselves to the universe through illumination and energy. A black hole, by absolute contrast, is defined entirely by what it lacks and what it hides. It has no solid surface, no material crust, no internal heat source of its own, and no light to share with the dark. It is completely invisible, hiding in plain sight against the black backdrop of space, revealing its presence only through the violent, chaotic distress of the surrounding matter that gets caught in its invisible grip. When we gaze into the deep picture of space-time distortion, black holes remind us that the stable stage of the universe can break, tear, and fold in upon itself in ways that defy human intuition. They are not merely massive stars gone dark, but permanent scars torn into the architecture of existence. They challenge our deepest assumptions about reality, forcing us to confront the limits of our understanding and the terrifying beauty of a universe that is far stranger, wilder, and more mysterious than our minds were ever evolved to comprehend. As we stand at the edge of this conceptual abyss, looking into the true nature of what a black hole is, we begin our descent into the deepest secrets of the cosmos. Surrounding the invisible core of a black hole lies one of the most profound and unforgiving boundaries in the entire universe: the event horizon. It is often visualized as a dark sphere floating in space, but it is not a physical surface, a solid wall, or a shell of matter that you could touch or crash into. Instead, the event horizon is a mathematical and physical threshold, a sharp line in the geometry of space-time where the rules of reality fundamentally change. It marks the exact point of no return, the invisible perimeter where the escape velocity required to break free from the black hole's gravitational pull exceeds the ultimate speed limit of the universe: the speed of light. To picture how this horizon forms, we must return to the concept of space-time as a flexible, stretching fabric. In the normal universe, mass creates a gentle depression in this fabric. If you roll a marble across a stretched rubber sheet with a heavy weight in the center, the marble dips into a curved path, but with enough speed, it can easily climb back out of the depression and escape into the wider sheet. As we move closer to a black hole, however, that gentle depression transforms into something vastly more extreme. The space-time fabric does not merely curve, it plunges downward into a vertical, bottomless pit. The closer you get to the center, the steeper the walls of this pit become, forcing light and matter to tumble faster and faster down its slope. The physical size of this boundary, known to physicists as the Schwarzschild radius, depends entirely on the mass of the black hole itself. A stellar mass black hole created from the collapse of a dying giant star might possess an event horizon measuring only a few kilometers across, compressing an entire sun's worth of matter into a sphere smaller than a modern city. On the other end of the scale, a colossal, supermassive black hole lurking at the center of a galaxy can feature an event horizon spanning millions of kilometers, wide enough to swallow entire planetary systems whole. Yet, regardless of whether the black hole is small or gargantuan, the fundamental geometry of the boundary remains identical: a razor-thin, inescapable precipice where space and time turn completely inward. At the precise boundary of the event horizon, the slope of this space-time pit becomes infinitely vertical. The curvature is so absolute and overwhelming that space itself flows inward toward the center at the speed of light. Imagine trying to swim upstream against a waterfall that is rushing downward faster than you can possibly paddle. No matter how strong you are, no matter how much thrust your engines possess, if your maximum speed is capped by the current, you are swept inexorably downward. For a photon of light, the fastest thing in existence, which normally cruises across the cosmos at nearly 300,000 kilometers per second. Crossing the event horizon means entering a current from which there is no escape. Light cannot travel outward, because outward no longer exists as a viable direction in space. Every possible vector of movement points deeper into the well. This strange geometry creates a profound optical illusion for anyone observing from a safe distance outside. Because gravity bends light so severely and stretches the fabric of time itself, an observer watching a clock or a spacecraft fall toward the event horizon would witness a bizarre phenomenon known as gravitational time dilation. As the falling object approaches the threshold, its clock appears to tick slower and slower relative to the outside universe. light signals sent upward from the spacecraft become heavily redshifted, stretched out into longer wavelengths until they fade into invisibility. To an outside watcher, the falling object never actually crosses the event horizon. Instead, it appears to slow down, freeze in place, and slowly fade into the dark, caught on the boundary like a photograph trapped in amber for eternity. Yet, the experience from the perspective of the falling object is entirely different and far more jarring. If you were to ride a spacecraft across the event horizon, you would feel no sudden jolt, no physical impact, and no dramatic wall preventing your passage. To your own instruments and your own experience of time, you would glide right across the threshold without even realizing the exact moment you pass the point of no return. You would cross the boundary in normal time, feeling the steady pull of acceleration, completely unaware that the bridge behind you has been permanently burned. Once you are inside, however, the reality of your situation becomes absolute. You are cut off from the rest of the universe, locked inside a one-way membrane of space-time, where every forward step in time brings you closer to the absolute center. As you descend further past the event horizon, the pit does not level off. It sharpens infinitely. The tidal forces generated by the extreme gradient of gravity begin to tear at the very fabric of matter itself. The gravitational pull on your feet, being fractionally closer to the center than your head, is vastly stronger than the pull on your upper body. This differential stretching force stretches any object vertically while compressing it horizontally, pulling atoms apart and shredding molecules into a thin stream of elementary particles. The space-time geometry grows steeper and more violent with every microsecond of descent, accelerating toward a final, infinite convergence where space and time cease to have any meaning at all. The event horizon stands as nature's ultimate barrier, a silent, unyielding guardian that hides the most violent and mysterious mechanics of the universe from our prying eyes. It protects the external cosmos from the chaotic infinity of the singularity within, while ensuring that whatever falls into its grasp is permanently erased from our reality. As we contemplate this steep, inescapable pit in space-time, we catch a glimpse of the terrifying elegance of black holes, where the geometry of the universe bends so completely that even light itself is swallowed by the dark. Beyond the event horizon, as you continue your unstoppable descent down the steep and narrowing well of space-time, you eventually run out of space altogether. You are heading toward the ultimate destination of a black hole, the final resting place of all the matter, energy, and light that fell into its grasp. This is the singularity, a point at the absolute center where the entire mass of a collapsed star is crushed down to a volume of zero. When you concentrate a massive amount of physical matter into a single mathematical point, with no physical dimensions, the result is a state of matter that defies comprehension. Infinite density. Every rule, law, and equation that scientists use to make sense of the universe grinds to a grinding, catastrophic halt at this exact location. To understand why the singularity represents such a profound crisis for human knowledge, we must look at how modern physics is constructed. For the past century, our understanding of the universe has rested upon two magnificent pillars of thought. The first is Albert Einstein's theory of general relativity, which describes the smooth, continuous geometry of space and time on a grand cosmic scale, explaining how massive objects warp the fabric of the universe to create gravity. The second is quantum mechanics, which governs the frantic, discrete, and probabilistic realm of subatomic particles, atoms, and molecules. Both theories are extraordinarily successful within their own domains, allowing us to build technologies like GPS satellites, predict gravitational waves, and understand the subatomic structure of matter with breathtaking precision. Yet when these two great theories are brought together at the heart of a black hole, they break down into complete contradiction. General relativity looks at the singularity and predicts that space-time curvature becomes infinite, density becomes infinite, and gravitational forces become infinitely strong. But in physics, the word infinity is not a real measurement or a physical quantity. It is a giant red flag. It is a mathematical confession that our equations have failed, that the model has collapsed, and that we no longer know what we are talking about. Nature does not tolerate infinities, and the appearance of them in our equations tells us that our understanding of reality is fundamentally incomplete. Quantum mechanics reacts to the idea of infinite density with an even stronger objection. According to the laws of quantum physics, subatomic particles cannot be squeezed into a zero-volume point without violating the fundamental uncertainty principle, which dictates that particles must maintain a minimum amount of positional and momentum wiggle room. If you try to crush matter down to a point of zero size, quantum forces should push back with incomprehensible violence, creating a pressure barrier that prevents complete collapse. Yet the immense gravitational weight of a stellar mass black hole is strong enough to completely overpower quantum pressure, crushing the atoms down until their internal structure is utterly erased. This direct conflict between general relativity and quantum mechanics is the greatest unsolved puzzle in modern theoretical physics. To truly understand what a singularity is, scientists need a bridge between the very large and the very small, a unified framework known as quantum gravity. Brilliant minds have spent decades developing hypotheses like string theory and loop quantum gravity, attempting to smooth out the infinite point of the singularity into something finite and manageable. In these advanced theoretical models, the singularity might not be a zero-volume point at all, but rather an unimaginably tiny, highly compressed quantum core, perhaps operating at the scale of the Planck length, where space and time themselves become a foaming, discrete quantum fabric rather than a smooth sheet. Yet, until we find a way to test these theories, a monumental challenge, given that the interior of a black hole is permanently sealed off from the outside universe by the event horizon. The singularity remains an absolute enigma. It sits at the very edge of human comprehension, a place where our language and mathematics run out of words. If you were to somehow survive the trip past the event horizon and approach the center, you would not find a hard, rocky surface or a glowing ball of metal. You would find a place where the dimensions of space and time completely lose their meaning, dissolving into a chaotic, formless state that exists outside of our ordinary physical reality. At the singularity, the normal flow of time that guides our everyday existence shatters into pieces. Time as a forward-moving dimension ceases to function, and space becomes a direction you can no longer escape, because every possible pathway through the geometry of the interior leads directly into the center. It is the end of the line, the absolute terminus of the timeline, for anything that crosses the threshold. Whatever information, history, or physical identity an object possessed when it entered the black hole is apparently crushed out of existence, stripped down to its most fundamental ingredients, and locked away in a state that defies our current understanding of information conservation in the universe. Physicists also grapple with a deeply unsettling question regarding whether singularities can ever exist nakedly, exposed to the open universe, without an event horizon wrapping around them. The prevailing cosmic censorship hypothesis suggests that nature abhors a naked singularity, always ensuring that an event horizon forms first to shroud the messy, law-breaking center away from the rest of the cosmos. If a naked singularity were ever to form, it would mean that the laws of physics could break down in plain view, creating a point in space where predictable cause and effect vanish entirely, allowing random, uncaused events to spill out into the wider universe and destroying the predictability of science itself. As we stand at the conceptual precipice of the singularity, peering into the deepest, darkest secret of the black hole, we are reminded of the profound humility required to study the cosmos. We live in a vast and intricate universe that operates on rules far deeper and stranger than our brains were originally shaped to fathom. The singularity is not just a mathematical anomaly or a morbid destination. It is the ultimate frontier of human curiosity, a quiet, hidden monument to the limits of our knowledge, waiting in the absolute center of the dark for a future generation of thinkers to finally unlock its impossible mysteries. To understand how these dark titans first enter our universe, we must leave behind the abstract geometry of space and look out into the glowing tapestry of the night sky, toward the fiery nurseries where giant stars are born, live, and eventually die. Every stellar mass black hole has a history, a violent and dramatic origin story rooted in the life cycle of a massive star that burned millions of light years away, or right in our own galactic neighborhood eons ago. These are not primordial monsters created at the dawn of the universe, but the direct descendants of individual suns that lived fast, burned bright, and collapsed under the crushing weight of their own mortality. During its normal lifetime, a massive star exists in a delicate and beautiful state of equilibrium. Deep within its blazing core, nuclear fusion acts as a continuous engine of creation, fusing hydrogen atoms into helium and releasing staggering amounts of thermal energy. This outward pressure of radiation and heat pushes relentlessly against the inward pull of the star's own immense gravity, holding the colossal sphere of plasma in a stable, shining balance for millions of years. But for stars that possess 10, 20, or 50 times the mass of our own Sun, this glorious existence cannot last forever. They consume their nuclear fuel at an astonishing rate, burning through their reserves with frantic intensity as they race toward a catastrophic destiny. Eventually, the inevitable moment arrives when the core of the giant star runs out of fusible material. When the nuclear fires begin to flicker and die, the outward thermal pressure that has held gravity at bay for millions of years suddenly vanishes in an instant. With no internal heat to support the star's colossal weight, gravity seizes absolute control. The outer layers of the star begin to fall inward toward the center with unimaginable speed, triggering a titanic collapse that unfolds in a fraction of a second. The core is compressed so violently that it rebounds in a colossal explosion known as a supernova, blasting heavy elements out across interstellar space in a blinding flash of light that can outshine an entire galaxy. Yet, while the outer layers are violently expelled into the cosmos, the innermost core suffers an even stranger and more terrifying fate. As the remnant core collapses, gravity crushes it past every known safety barrier in nature. In a normal, stable atom, electrons orbit a dense nucleus with vast expanses of empty space separating them, creating a structural rigidity that resists compression. But the raw, unyielding gravity of a collapsing massive star easily overpowers this electron degeneracy pressure, forcing the electrons directly into the atomic nuclei, where they merge with protons to form a dense sea of neutrons. If the remaining mass is modest, this creates a neutron star, a city-sized sphere of matter so dense that a single teaspoon of it would weigh billions of tons on Earth. However, if the collapsing core exceeds a critical mass threshold, known as the Tolman-Oppenheimer-Volkoff limit, even neutron degeneracy pressure fails entirely. There is no force left in the universe capable of stopping the collapse. The neutrons are crushed, the internal space within the subatomic particles is erased, and the entire mass of the core plunges inward toward a single, microscopic point. A massive star that once spanned millions of kilometers across, glowing with the light of billions of candles, is compressed into an object so tiny that its physical volume effectively vanishes, leaving behind a stellar mass black hole wrapped inside its newly formed event horizon. The sheer scale of this compression is almost impossible for the human mind to comfortably visualize. Imagine taking a colossal star containing the weight of 20 suns, a blazing, magnificent giant that dwarfs our entire solar system, and squeezing every single atom of its physical substance down into a sphere no larger than a modern city, or even a microscopic point. The density defies all everyday intuition. You have taken a massive, sprawling volume of space and concentrated its entire heavy essence into an invisible speck that floats silently in the dark. Despite their minuscule physical dimensions, stellar mass black holes possess an immense gravitational weight that commands absolute authority over their immediate surroundings. If our Sun were somehow compressed into a black hole of identical mass, its event horizon would span a mere 6 kilometers across, about the size of a small town. Yet, its gravitational pull on the planets would remain completely unchanged. Earth would continue orbiting that tiny, invisible point of darkness in the exact same path it follows today. The black hole does not need to be physically large to exert its immense influence. Its power comes entirely from the absolute concentration of its mass within a severely warped patch of space-time. Across the Milky Way, billions of these stellar corpses drift silently through the dark, hidden monuments to ancient stellar deaths. Most of them remain entirely invisible to our telescopes because they travel through empty interstellar space, far away from any source of gas or companion stars to feed upon. They are quiet, solitary ghosts of giants moving through the void with no light to guide them and no sound to mark their passage. They wait patiently in the blackness, reminding us of the violent forces that shaped our galaxy long before humanity ever looked up to wonder at the stars. As we contemplate these stellar mass titans, we begin to realize the true economy of the cosmos. Matter and energy are constantly recycled, transformed from blazing plasma into invisible points of infinite density, bridging the gap between the birth of stars and the deepest mysteries of space. They are the compact, heavy anchors of our galactic neighborhood, holding together the delicate balance of the systems around them while guarding the secrets of their violent births behind a veil of absolute darkness. Long before our modern telescopes could ever hope to capture a glimpse of the dark. Black holes existed only as shadows in human mathematics, wild, theoretical concepts sketched out by brave pioneers who dared to push the laws of physics past their breaking points. For centuries, the idea of an object so dense and heavy that even light could not escape its grip was treated as a mathematical curiosity, a science fiction thought experiment born from the deepest reaches of theoretical calculus. The history of how humanity uncovered these invisible monsters is a sweeping tale of intellectual courage, spanning centuries of skepticism, mathematical breakthroughs, wartime calculations, and ultimately, modern technological triumphs that brought the invisible out of the dark. The conceptual seeds of the black hole were planted long before Albert Einstein ever wrote down his field equations, stretching all the way back to the late 18th century. In 1783, an English clergyman and natural philosopher named John Michell wrote a brilliant letter to the Royal Society applying Sir Isaac Newton's laws of gravity and corpuscular light theory to imagine a radical possibility. Michell calculated that if a star were compressed down to a sufficiently small size while maintaining a massive amount of weight, its escape velocity would equal or exceed the speed of light. Light emitted from such a star would be pulled relentlessly back down by gravity, rendering the object entirely invisible to the outside universe. A few years later, the French mathematician Pierre-Simon Laplace independently arrived at the exact same conclusion in his famous book Exposition du Système du Monde. These visionary thinkers called them dark stars, recognizing that gravity could potentially build a cage from which not even illumination could flee. Yet, these early 18th century ideas were little more than mathematical toys. Newton's physics lacked the necessary framework to truly describe what happens to space and time under such extreme conditions. The true birth of the modern black hole had to wait until November 1915, when Albert Einstein published his revolutionary theory of general relativity. Einstein replaced Newton's invisible pulling force with a dynamic, flexible fabric of space-time, showing that mass dictates how space curves and bends. Just weeks after Einstein published his field equations, a German physicist and astronomer named Karl Schwarzschild found an exact solution to those complex equations while serving on the Russian front during World War I. Working under the harrowing conditions of an artillery trench, Schwarzschild solved Einstein's equations for a single, spherically symmetric mass. The result of his calculations revealed a terrifying mathematical boundary, a precise radius where space-time curvature becomes infinite and the equations break down entirely. This threshold, which would later be named the Schwarzschild radius in his honor, mapped out the exact size of the event horizon for any given mass. Tragically, Schwarzschild contracted a rare skin disease while on the front lines and passed away just months after his discovery, never living to see how deeply his trench-side calculations would transform our understanding of the cosmos. Despite the elegance of Schwarzschild's math, for decades many of the world's leading physicists, including Einstein himself, refused to believe that such monstrous objects could actually form in the real universe. They viewed the Schwarzschild radius as a mathematical artifact, a quirky quirk of the equations that nature would surely find a way to prevent. Even as theoretical work in the 1930s by scientists like Subrahmanyan Chandrasekhar and Robert Oppenheimer mathematically proved that collapsing massive stars must inevitably crush themselves into gravitational singularities, the scientific community remained deeply skeptical. The term black hole itself did not enter the popular lexicon until late 1967, when the legendary physicist John Archibald Wheeler popularized the name during a lecture, replacing clunkier historical terms like gravitational collapse, singularity, with a phrase that perfectly captured their mysterious nature. Proof that these dark entities were not just mathematical fantasies began to emerge during the dawn of the space age in the 1970s, through the birth of X-ray astronomy. Satellites launched above Earth's filtering atmosphere detected powerful, high-energy X-ray sources blazing from deep space. One of the very first and most convincing candidates was Cygnus X1, a binary star system where a luminous blue supergiant was observed orbiting an invisible, massive companion. By tracking the frantic orbital speed of the visible star, astronomers calculated that its unseen partner possessed a massive weight concentrated into a space far too small to be a normal star. It was the first undeniable smoking gun, an invisible gravitational anchor pulling on matter, confirming that stellar mass black holes were actively roaming our galaxy. As decades passed, indirect evidence accumulated on a staggering scale. Astronomers peered into the chaotic hearts of distant galaxies and detected mysterious, colossal forces, keeping billions of stars locked in tight orbits around invisible centers, pointing toward the existence of supermassive black holes. Yet despite mounting mathematical and indirect proof, no one had ever actually seen one. Capturing an image of a black hole was long considered an impossible dream, akin to trying to photograph a grain of sand on the surface of the moon from the comfort of Earth. The event horizons were simply too small, too distant, and wrapped in too much cosmic dust and glowing gas to resolve with traditional telescopes. That insurmountable barrier was finally shattered in April 2019, when the Event Horizon Telescope collaboration released the first direct visual confirmation of a black hole. By linking a global network of radio observatories spanning from the frozen peaks of Antarctica to the volcanoes of Hawaii and the deserts of Spain, scientists created a virtual Earth-sized telescope with the resolving power needed to peer into the heart of the distant galaxy M87. What appeared on computer screens around the world was not a pitch-black circle, but a breathtaking glowing orange ring of hot, swirling plasma framing a deep, unmistakable shadow. The event horizon itself, casting its shadow against the brilliant accretion disk. In 2022, the collaboration struck again, revealing the first image of Sagittarius A star, the supermassive black hole lurking quietly at the center of our own Milky Way. The journey from John Michel's 18th century dark stars and Carl Schwarzschild's wartime calculations to the glowing orange rings captured by the Event Horizon Telescope stands as one of the greatest triumphs of human intellect. We moved from pencil and paper equations sketched in the mud to the cutting edge of global astronomy, proving that the wildest, most terrifying predictions of theoretical physics are living realities in our universe. As we look at those images of the dark, we are reminded of how far our curiosity has carried us, and how much mystery still waits in the quiet depths of space. Far beyond the quiet outer fringes of our solar system, and deeper than the stellar mass corpses that drift through the dark arms of the Milky Way, lies a class of cosmic royalty so colossal, so terrifyingly powerful, that they reign as the undisputed kings of the universe. These are the supermassive black holes, monstrous titans that sit enthroned at the very centers of almost every major galaxy in existence. While stellar mass black holes are born from the collapse of individual giant stars, measuring a few miles across and weighing a handful of suns, supermassive black holes are an entirely different breed of cosmic architecture. They contain the weight of millions or even billions of solar masses, compacted into regions of space that can span the distance from the Earth to the Sun or beyond. They are the anchor points of creation, the gravitational heartbeats that pulse at the center of island universes containing hundreds of billions of shining stars. To comprehend the sheer scale of a supermassive black hole, we must look inward toward the heart of our own galaxy. Tucked away behind dense clouds of cosmic dust in the constellation Sagittarius. There, resting quietly about 26,000 light-years from our home, lies Sagittarius, a star, a gentle giant, weighing roughly 4 million times the mass of our Sun. For decades, astronomers tracked the frantic, looping orbits of stars whipping around an entirely empty point in space at speeds of millions of miles per hour, proving beyond a shadow of a doubt that a massive gravitational anchor was holding the galactic core together. When the Event Horizon Telescope finally captured its image in 2022, it revealed a glowing ring of superheated gas, framing a dark, shadowy silhouette, the event horizon of our local king quietly overseeing the swirling spiral arms where our solar system resides. Yet, as massive as Sagittarius A star is, it is practically a lightweight compared to the true leviathans that lurk in the centers of other galaxies across the cosmos. In giant elliptical galaxies, where stars are crammed together by the trillions, the central black holes grow to unfathomable proportions. Consider M87, a colossal galaxy sitting at the heart of the nearby Virgo cluster. Its central black hole possesses a mass equivalent to 6.5 billion suns, creating an event horizon so expansive that it could easily swallow our entire solar system whole, with room to spare. And these pale in comparison to record breakers like TON 618, an ultramassive black hole sitting at the center of a distant quasar, estimated to weigh a staggering 66 billion times the mass of our Sun. Its event horizon alone spans a distance of hundreds of billions of kilometers, a dark empire of gravity so immense that it stretches far beyond the conventional boundaries of what we expect a single object to be. How these impossible monsters grew to such colossal proportions remains one of the greatest and most fascinating debates in modern astrophysics. When we look back deep into the early universe using powerful tools like the James Webb Space Telescope, astronomers have discovered something deeply shocking. Supermassive black holes existed much earlier in cosmic history than our standard models predicted. They were already massive when the universe was only a few 100 million years old, leaving scientists scrambling to figure out how they could have accumulated so much mass so quickly. The traditional theory of gradual growth, where a smaller stellar mass black hole slowly feeds on passing gas and stars over billions of years, cannot account for how these giants got so big, so fast. Instead, astronomers believe these early kings may have been born through more violent and dramatic mechanisms in the primordial universe. Some models suggest they formed from the direct, catastrophic collapse of massive, pristine gas clouds in the early cosmos. Bypassing the stellar phase entirely to create massive seed black holes, weighing 10,000 to 100,000 suns right from the start. Once these heavy seeds were planted, they engaged in epic cosmic feasts, merging with other black holes during violent galactic collisions and gorging themselves on rivers of primordial gas streaming through the dense, unformed galaxies of the young universe. These feeding frenzies turned the centers of ancient galaxies into blinding beacons of light known as quasars, which shone brighter than 1,000,000,000,000 stars combined, casting illumination across the dark expanse of early space. This brings us to one of the most profound realizations in modern astronomy. Galaxies and their central supermassive black holes are locked in a deep, lifelong symbiotic relationship. For a long time, scientists viewed black holes as passive passengers riding along inside the larger structure of a galaxy. But we now know that the supermassive black hole acts as the master regulator of the entire system. When it feeds on surrounding gas, the extreme friction and magnetic forces in its accretion disk generate powerful winds and relativistic jets of energy that blast outward into the galaxy. This titanic outflow can heat up or sweep away the cold gas clouds required to form new stars, effectively acting as a cosmic thermostat that controls whether a galaxy lives or dies. If the black hole feeds too fast, it starves its own galaxy of star-making material, causing star formation to grind to a halt. If it sleeps, the galaxy blooms with new stellar nurseries. Beyond individual galaxies, supermassive black holes play a vital role in shaping the grand cosmic web that spans the universe. As galaxies drift along invisible filaments of dark matter, they frequently encounter one another, leading to majestic and cataclysmic galactic mergers. When two galaxies collide, their central supermassive black holes spiral inward toward each other over hundreds of millions of years, locked in a decaying dance driven by the emission of gravitational waves. When they finally merge into an even greater titan, they send ripples through the fabric of space-time itself, shaking the universe with an invisible tremor that we can now detect across the void. The king at the center dictates the destiny of the entire empire. Every star in the Milky Way, every glowing nebula, and every distant world is tethered to the gravitational heartbeat of Sagittarius A star, moving in a grand, harmonious dance around a hidden core of absolute darkness. These supermassive black holes are not just cosmic anomalies or destructive monsters waiting to devour matter. They are the architectural anchors of the universe, the heavy stones at the center of the arch that hold the glorious tapestry of galaxies together. As we gaze out across the cosmic web, tracing the glowing spirals of distant island universes, we are always looking toward the quiet, powerful gaze of the king resting in the dark, holding the galaxy in his eternal, invisible embrace. While the event horizon and the hidden singularity deep within are cloaked in absolute, impenetrable darkness, a black hole in the real universe is rarely a quiet or lonely phantom. In fact, when we look at these cosmic titans through the lenses of our most powerful space telescopes, we discover that they are often surrounded by some of the most violent, blindingly brilliant spectacles in all of creation. This roaring, incandescent maelstrom of matter is known as an accretion disk. It is a swirling, cosmic whirlpool of gas, dust, and shredded stellar debris trapped in the gravitational grip of the black hole, spinning at unfathomable speeds as it prepares to cross the ultimate threshold of no return. To truly picture an accretion disk, we must abandon any simple idea of a clean, straight fall into the abyss. When a massive cloud of interstellar gas or an unfortunate wandering star drifts too close to a black hole, it does not plunge directly down the center like a stone dropped into a well. Because everything in the universe carries angular momentum, a natural tendency to spin and orbit, the incoming material is caught up in a grand orbital dance. As it gets closer to the event horizon, gravity accelerates the material to breathtaking fractions of the speed of light, forcing it to flatten out into a swirling, circular disk that can span millions of kilometers across the dark expanse of space. Within this colossal cosmic traffic jam, the physics taking place are nothing short of apocalyptic. The inner edges of the disk are subjected to extreme gravitational gradients, causing different parts of the disk to spin at wildly different speeds. The inner rings whip around the black hole at nearly the speed of light, while the outer edges move more sluggishly. This differential rotation creates violent friction on a scale that defies imagination. Trillions of gas atoms and dust particles slam into one another at relativistic velocities, generating massive shock waves, intense magnetic fields, and unimaginable thermal energy. The temperature inside the disk skyrockets into the millions of degrees, turning ordinary gas into a glowing, superheated plasma of ions and electrons. This intense friction and compression act as a cosmic power converter, transforming the raw gravitational potential energy of the falling matter into blazing radiation. The accretion disk begins to glow with a blinding fury, emitting floods of ultraviolet light, X-rays, and gamma rays that pierce through the darkness of space. In the case of supermassive black holes feeding voraciously in the centers of young galaxies, these blazing disks become known as quasars, beacons of light so profoundly luminous that they can outshine every single star in their host, galaxy combined, casting their brilliant illumination across billions of light years of cosmic space. Yet the visual appearance of an accretion disk is further complicated by the extreme warping of space and time that surrounds the black hole. Because the gravitational field is so overwhelmingly strong, it acts as a massive optical lens, bending the rays of light emitted by the disk in bizarre and counterintuitive ways. If you were to look at a black hole from a safe distance, you would not just see the front face of the glowing disk spinning across your field of view. The bending of space-time curves the light from the back of the disk up and over the top of the black hole and down underneath it, creating a luminous halo that completely frames the central shadow. Furthermore, because the material in the disk is spinning toward us on one side and away from us on the other at near-light speeds, a phenomenon known as relativistic Doppler beaming takes place. The side of the disk rotating toward our viewpoint appears dramatically brighter and shifted toward the blue end of the spectrum, while the side spinning away from us is dimmed and shifted toward the red. This creates a striking asymmetrical appearance, a brilliant crescent-shaped blaze of light wrapping around a stark, pitch-black sphere, exactly matching the iconic silhouettes captured by the Event Horizon Telescope in recent years. Despite the blinding brilliance of the accretion disk, it is important to remember that it is not a permanent fixture, but rather a temporary feeding ground. The material within the disk is caught in a slow, agonizing descent. As friction robs the particles of their orbital energy, they spiral inward, creeping closer and closer to the event horizon over thousands of years, until they finally cross the threshold and disappear forever into the dark. The black hole feeds on this continuous supply of matter, slowly growing in mass while the disk itself is constantly replenished by new gas, streaming in from the surrounding galaxy. Not all of the matter in the disk makes it past the event horizon, however. The intense magnetic fields twisting through the superheated plasma act like a cosmic particle accelerator, capturing a fraction of the incoming gas and funneling it away from the disk entirely. This material is accelerated outward along the rotational poles of the black hole, shooting twin beams of high-energy plasma called relativistic jets miles or even light years out into space. These colossal jets pierce through galaxies like massive blowtorches, regulating the temperature of surrounding gas clouds and proving that even as a black hole feeds in silence, its fiery dining room exerts a powerful influence on the entire universe around it. The accretion disk represents a masterclass in cosmic contrast, a zone where absolute destruction and dazzling creation exist side by side. It is the brilliant, roaring crown worn by the silent king of the dark, a swirling vortex of energy that transforms the silent tragedy of falling matter into a magnificent fireworks display visible across the universe. As we gaze upon the glowing energy rings that feed these hidden giants, we are reminded of the raw, untamed power that shapes the architecture of space, turning the violent end of matter into one of the most stunning sights in all of nature. For centuries, science viewed black holes as absolute and eternal prisons, permanent monuments of darkness that could only grow larger as they swallowed surrounding matter, never losing a single fraction of their mass. Once something crossed the event horizon, it was locked away for all time, and the black hole itself seemed destined to endure long after every star in the universe had burned out and died. But in the 1970s, the brilliant physicist Stephen Hawking unlocked a startling and counterintuitive truth that shattered this illusion of permanence. He discovered that black holes are not entirely black at all, and they do not live forever. Through the strange and chaotic rules of the subatomic world, they are slowly, quietly bleeding away into the cosmos, locked in a multi-trillion-year process of ghostly evaporation known as Hawking radiation. To understand how a black hole can lose weight, we must leave behind the smooth, predictable geometry of Einstein's general relativity and venture into the frantic, unpredictable realm of quantum mechanics. In our everyday experience, empty space is a vacuum, a total absence of matter and energy. But at the microscopic subatomic scale, empty space is never truly empty. According to the laws of quantum physics, the vacuum is a boiling, restless sea of energy where virtual particle-antiparticle pairs constantly flicker into existence out of nothingness. A particle and its antimatter twin pop into being side by side, exist for a fleeting fraction of a second, and instantly collide with one another, annihilating back into pure energy in a continuous, invisible dance across the universe. Normally, this quantum shimmering happens out in the open cosmos, cancelling itself out instantly and leaving no net change in the surrounding environment. But at the razor-thin boundary of a black hole's event horizon, the rules of this quantum theatre change in a profound and radical way. When a virtual particle-antiparticle pair flickers into existence right on the precipice of the horizon, the extreme gravitational gradient can split them apart before they have a chance to annihilate. One of the particles is dragged relentlessly downward across the event horizon, tumbling into the inescapable pit of the singularity, while its partner is left stranded just outside the boundary in the open universe. Unable to recombine with its twin, the surviving particle is propelled outward away from the black hole, escaping into deep space as a real, physical particle of thermal radiation. To an outside observer watching from a safe distance, the black hole appears to be glowing with a faint, ghostly whisper of heat and light. This is Hawking radiation. It is a slow, steady leakage of energy emitted from the very edge of the abyss, transforming the ultimate trap into a leaking vessel that slowly bleeds its contents back into the universe. Yet, this process carries a profound physical cost for the black hole itself. In the universe, energy and mass are strictly conserved. Nothing can be created from nothing. The particle that escapes into space carrying thermal energy cannot simply materialize out of thin air. To pay the energetic price for that escaping particle, the black hole must surrender a tiny fraction of its own mass energy. The particle that fell inward across the horizon carries a negative energy relative to the outside universe, subtracting from the total mass of the black hole. In essence, every time a particle of Hawking radiation escapes, the black hole shrinks just a microscopic fraction of a millimeter, losing a tiny sliver of its immense weight. The rate at which this evaporation occurs, however, is unimaginably slow. For a typical stellar mass black hole created from the collapse of a giant star, the emission of Hawking radiation is so faint and sluggish that it is entirely swallowed up by the cosmic background radiation of the universe, because the black hole is constantly bathed in the leftover heat of the Big Bang and occasionally snacks on stray atoms of gas drifting through space. It actually gains mass much faster than it loses it through evaporation today. A stellar mass black hole is currently growing, not shrinking, because the ambient temperature of the universe is higher than the microscopic temperature of its Hawking radiation. Only when the universe expands further, cooling down over unfathomable spans of future time as the stars fade and galaxies drift apart, will the ambient temperature drop low enough for Hawking radiation to take the lead. Once that distant era arrives, the slow decay of black holes will truly begin in earnest, though the timescale required for a black hole to completely evaporate is so vast that it defies human intuition. A stellar mass black hole will take not millions or billions, but a Google years, a one followed by 100 zeros, to fully evaporate into nothingness. During this unimaginable expanse of deep time, the black hole will slowly shrink, its temperature rising higher and higher as it loses mass, until it enters a frantic, runaway phase of collapse. In the final, dramatic microsecond of its existence, an evaporating black hole experiences a terminal burst of energy, releasing a blinding flash of high-energy gamma rays before vanishing completely from space-time, leaving behind nothing but an empty pocket of space where a titan once stood. This startling reality means that no black hole in the universe is truly eternal. The most powerful, colossal, supermassive black holes anchoring the centers of galaxies, which reign as kings of the dark for eons, are ultimately mortal, bound by the patient, unyielding erosion of quantum mechanics. Even they will eventually fade away, returning their mass to the cooling cosmos as a final silent whisper of energy in the dark. While we often picture galaxies as isolated island universes, drifting peacefully through the endless dark, the reality of the cosmos is far more dynamic and interconnected. Across billions of years, galaxies do not remain permanently separated. They are drawn toward one another by the massive, invisible web of gravity, drifting along cosmic filaments until their paths inevitably cross. When two massive galaxies collide, they do not smash together like rigid stones. Because stars are separated by immense expanses of empty space, the two galaxies pass right through each other in a slow, ghostly intermingling where individual stars rarely touch. Yet, hidden deep at the core of each colliding galaxy lies its ultimate anchor, a colossal, supermassive black hole. As the two island universes merge into a single magnificent structure, their central kings are dragged inexorably toward a common center, setting the stage for one of the most violent and awe-inspiring cataclysms the universe has ever known. This cosmic dance begins long before the black holes actually meet, unfolding over hundreds of millions of years as the outer structures of the galaxies first interact. As the gas clouds, dust, and stars tidal wave into new configurations, the two supermassive black holes are pulled toward the common center of gravity of the newly forming system. Through a complex gravitational process known as dynamical friction, the black holes plow through the surrounding sea of stars, transferring their orbital energy to the passing matter. This energy loss causes their orbits to slowly decay, spiraling inward in an ever-tightening celestial orbit as they inch closer and closer together across the span of millions of years. For a long time, astrophysicists puzzled over a major theoretical roadblock in this process known as the final parsec problem. According to computer models, as the two supermassive black holes approach each other and reach a distance of about 1 parsec, roughly 3 light-years apart, the dynamical friction from surrounding stars starts to taper off. Without a way to shed their remaining orbital energy and angular momentum, the two black holes should theoretically stall out, locked in an eternal, permanent embrace just shy of collision. Yet, observations proved that supermassive black holes do merge, meaning nature found a clever way around this bottleneck. The chaotic influx of gas streaming into the collision zone, or the gravitational influence of a third passing body, helps bleed off the final bit of angular momentum, driving the two titans past the invisible barrier and into their final, fatal descent. As the two black holes cross that final threshold, the physics of their interaction shifts from a slow orbital decay into a terrifyingly rapid plunge. At this stage, they are no longer just orbiting a mutual center of gravity. They are accelerating toward each other at breathtaking fractions of the speed of light. Distortion, wrapping around them as space-time begins to buckle under the strain. The sheer mass of the two approaching horizons creates extreme gravitational gradients that warp the surrounding space into a churning, chaotic soup of high-energy radiation. The accretion disks surrounding them clash and merge, flooding the surrounding galaxy with brilliant flares of light and energy as the final countdown to impact begins. The actual moment of merger is a quiet spectacle in terms of visible light, but a cataclysmic explosion in the invisible fabric of space-time. When the two event horizons touch and fuse into a single, larger black hole, they do not create a flash of starlight or a fiery blast of plasma. Instead, they unleash a titanic storm of gravitational waves. As predicted by Albert Einstein a century earlier, the violent collision of masses moving at near light speed sends powerful ripples rolling outward through the geometry of space. These gravitational waves sweep across the universe at the speed of light, stretching and squeezing the very fabric of the cosmos as they travel, carrying away a significant fraction of the combined mass energy of the black holes in a blinding microsecond of pure, raw space-time vibration. The newly formed supermassive black hole that emerges from this collision is a single, majestic titan, but it bears the physical scars of its violent birth. Because the two original black holes approached each other with unequal masses or asymmetric spins, the gravitational waves emitted during the final merger are unevenly distributed in one direction. This imbalance creates a powerful, invisible recoil effect known as gravitational rocket kick. The newly merged black hole can be physically recoiled, kicked off its central resting place in the galaxy at speeds of thousands of kilometers per second. In some rare and extreme cases, this kick is strong enough to eject the supermassive black hole entirely out of its host galaxy, sending the Silent King wandering through intergalactic space as a rogue giant, trailing an orphaned cluster of stars in its wake. Most of the time, however, the kick is gentle enough that the newly minted supermassive black hole settles back down into the heart of the merged galaxy, absorbing its new mass and growing even more powerful than before. It resumes its quiet vigil, re-establishing its gravitational dominance over the surrounding stars and gas, holding the newly unified galaxy together in a single, harmonious system. These titanic mergers are not merely destructive events of cosmic violence. They are the primary engines driving the growth of supermassive black holes across the history of the universe, shaping the evolution of galaxies and proving that even the most massive objects in existence are constantly being rewritten by the grand, sweeping movements of the cosmos. As we watch these invisible giants collide in the dark, we witness the ultimate architecture of space reshaping itself in real time, bridging the gap between individual stars and the grand, evolving tapestry of the universe. As we reach the final chapter of our cosmic journey, we must look far beyond the immediate horizon of our current era, past the birth and death of stars, and deep into the ultimate future of the universe itself. For billions of years, the night sky has been a brilliant tapestry of shining stars, glowing nebulae, and blazing galaxies, giving us a comforting illusion of permanence. But astronomy teaches us that everything in the cosmos has a lifespan. Stars are engines of consumption that must eventually exhaust their fuel. As we gaze into the deep future, we find ourselves approaching an era where the lights of the universe begin to go out one by one, leaving behind a cold, quiet expanse where only the ultimate survivors remain. This distant epoch, known to astronomers as the degenerate era, will begin when the last stellar nurseries run out of gas and the final generation of stars flickers and dies. Over trillions of years, red dwarfs will exhaust their hydrogen, white dwarfs will cool into cold, dark cinders of carbon and oxygen, and neutron stars will fade into absolute chill. The vibrant, glowing galaxies that populate our night skies will dissolve as their stellar populations are either flung into the intergalactic void or swallowed by the centers of their systems. The era of starlight will draw to a close, replaced by a dark and freezing universe, where nuclear fusion is nothing more than an ancient memory. Yet even as the stars vanish and the cosmos plunges into eternal night, the universe is not entirely empty. Lurking in the center of what used to be galaxies, and drifting quietly through the vast, dark spaces between them, are the black holes. Having outlived every star, planet, and nebula, these silent titans inherit the universe. They become the absolute masters of the dark, holding the remaining mass of the cosmos within their invisible, inescapable grip. for an unfathomable span of time, measured in timescales that stretch far beyond human comprehension. Black holes will reign supreme over a silent, cooling empire, drifting alone across an expanding void. During this solitary reign, the universe will enter the black hole era. It is a strange and surreal chapter of cosmic history where almost all matter in existence is locked away inside the event horizons of black holes or wandering as cold, dead fragments of degenerate matter. There is no warmth, no light, and no dynamic stellar chemistry left in the wider universe. The cosmos becomes a vast, dark ocean where black holes are the only active entities remaining, slowly orbiting one another across unimaginable distances in the freezing dark, continuing their ancient dance long after the rest of creation has grown old and still. Yet, as we discovered in our exploration of quantum mechanics and Hawking radiation, even these monumental survivors are not truly eternal. Bound by the relentless and patient rules of the subatomic world, every black hole in the universe is engaged in a slow, multi-trillion-year process of ghostly evaporation. Molecule by microscopic molecule, particle by escaping particle, they bleed their mass energy back out into the freezing cosmos. As the ambient temperature of the expanding universe drops closer and closer to absolute zero, the rate of Hawking radiation begins to take effect, initiating the very slow, agonizing decay of the final giants. This evaporation process takes a duration of time so vast that human numbers begin to lose all practical meaning. We must speak in terms of googles of years, numbers so enormous that they dwarf the current age of the universe by factors of unimaginable magnitude. During this incomprehensible span of deep time, the supermassive black holes that once anchored great empires of stars will slowly shrink, their event horizons contracting year by year, century by century, as their internal mass is converted into a faint, thermal whisper escaping into the dark. In the final, dramatic microsecond of their existence, these evaporating titans will experience a terminal flash of high-energy radiation, releasing the last remaining reserves of their mass before vanishing completely from space-time. When the very last black hole in the universe finally dissolves into a formless mist of photons and elementary particles, the history of matter as we know it comes to an absolute end. The universe enters the Iron Era and eventually the Dark Era, a state of infinite expansion where photons travel endlessly through an immense freezing void, never hitting another obstacle, never creating another spark of life. It is a profound and humbling thought, reminding us of the ultimate fragility and transient beauty of everything we see around us today. Yet, there is a strange, quiet peace in this cosmic perspective. The matter that makes up our world, our bodies, and the stars in our sky has been part of this grand, endless cycle of transformation since the dawn of time, and it will continue to drift through the universe long after our era has passed. As we conclude our journey through the mysteries of black holes, we can let our bodies sink deeper into the quiet night, letting go of the noise of the day and allowing our minds to rest in the vast, beautiful, and eternal silence of the cosmos.